Well, that's obviously a very, very difficult act to follow. Both of those acts are very difficult acts to follow. So I'm going to give a little bit more of sort of the technical side of what we've been talking about and a bit of what we've been doing. Talking about the 2021 mission. Of course, we worked a lot on the 2018 mission, and the report is out. One of the interesting things for me was just how much Mars really is in the zeitgeist of the world. We had 4 billion media impressions from the work that basically said, we've got an idea for a trajectory for a mission. So there's a lot of popular support, and I've gotten a lot of comments from people who said, well, it's really not that inspiring, you're just flying by. Well, Apollo 8 broke viewership records, and so flybys really are compelling. The architecture, as I'm sure you all know by now, was basically launched with an SLS, with a habitat in a small capsule. Use any commercial crew vehicle to get the crew to it. This was simply because we didn't want to have a NASA-involved mission that didn't have crew escape. So you could very easily just launch the crew in that module and go on a direct descent. The whole point of commercial crew is simply to avoid the launch without crew escape and do the trajectory that you heard so much about today. So there were several issues with it, and all the teams dealt with these issues as best they could. High entry speeds, it's a 2-launch, or we've seen 3 launch scenarios. Dependency in the commercial crew program and it getting done on time. Obviously dependency on SLS, and of course, the 2018 launch date. The 2021 mission really resolves a lot of these issues. We have a single launch scenario, which I'll show you. We use Orion for the mission because there's lower entry speeds. We've got a bit more time. We're getting a lot of backing in DC, which has been very interesting to watch occur and help along. This very rare opportunity of a Venus swing by as a kicker to the mission, and it's only 80 days longer. The trajectory is you've seen somewhat today, leaves Earth, goes by Venus, and then swings out to Mars and back. 133 days to the Venus swing by. We're at 324 for the Mars swing by, and then back onto Earth. The configuration is, and one of the things that really excites me about this configuration is I think it's finally a mission worthy of the Orion and SLS programs. We are investing in these amazing spacecraft, but I've yet to really see, what's the mission that gets them through the administration change? What's the mission that compels us to get them through all the political foils that are going to happen as we develop these vehicles? And so I think it's critical that we have compelling missions for these vehicles. And I'm sure I'm just singing to the choir for a lot of people. He had to have the mission selfie. You can lay out a sequence that actually makes some sense in the development of SLS. Using EM1 obviously is a test flight. EM2 is the first human flight with SLS and Orion. EM3 is the 2021. You can throw EM4 in between, doing an asteroid mission, which is, I think there's a lot of great parallels to this. And so it's not incongruent with the sequence that we're seeing with these flights anyway. And I think that's an important aspect to it. And as we said, well, it's a partnership, how does this work? I think it's astounding, the level of flexibility and rapidly changing paradigms that we've seen in NASA for, this is a federal bureaucracy, right? It was not too long ago when I know people in the ISS program who were saying there will never be a commercial anything anywhere near the approach ellipse for ISS. You've got to be kidding, right? And now we've seen it a couple of times. The change can and does happen in this organization, often by necessity, but I think we underestimate the potential for change in operating paradigms to occur in NASA. And fundamentally, NASA is a philanthropy, right? So it is really quite natural for NASA to team with other philanthropies. This actually makes a lot more sense in some ways than teaming with commercial entities. So teaming with a philanthropy like the Inspiration Mars Foundation actually, I think makes a lot of sense. So in a scenario, we've seen many scenarios today, NASA enters into a public-private partnership with Philanthropies. What's interesting about that is that major universities raise $1 to $5 billion in a capital campaign routinely. Little old University of Arizona, Southern Arizona, is in the middle of a $1.5 billion capital raise, and they raised $1.2 billion the last time they did a capital raise. $5 billion raises are really quite routine. So these numbers actually aren't out of norm for a philanthropic campaign that involves public institutions like NASA. Obviously, NASA retains key functions. You figure out what's the best roles in the partnership. You know, maybe husband and wife team. What was interesting when we were on the Hill about the husband and wife team is how much the family values folks really love that idea. Don't underestimate the value of that idea in the message that it sends to people who aren't naturally in the constituency. And of course, the foundation and others contributes concept advocacy, EQUIS, and things like that. Arm-waving numbers, these are not validated, but some quick work we've been doing. We've got the Orion capsule, which Michael's going to get lighter and lighter for us, I'm sure. The service module gets mostly stripped out because you don't need a lot of what's in the service module, but it's mostly a removing of functionality, but it's still, we still need the European service module, a habitat module of some sort. I think where we differ from a lot of what we saw today was this is really sort of the Lewis and Clark stripped down. You are not in a big volume. This is a rough mission. This is not a luxurious flight. And also we obviously have to adapt to the SLS, which is always a strikingly large amount of mass. This is another essentially picture of the same configuration, but showing how it all stacks up. In a stack configuration that is not unnatural to SLS. And so I think we're really still in the vein of what SLS and Orion configurations can and should do. There's a couple of options for the habitat and MPLM-based or the PCM-based options that we saw a lot of today. And these aren't a bad size. This is the MPLM inside. When you really can use all the dimensions, as Dennis was saying, these are big volumes. And I think we have to really question, we go on and on about, there's this line in a NASA study that was done 30 odd years ago or something that says this is the tolerable line. There's never really been a microgravity study or any real study that proves that's the tolerable line. It just becomes verbatim. It actually turns out to be very, very difficult to get references to the NASA human standards, the 3,000, 5,000 standards for human. We actually tried as part of these Space Act agreements. Show me the basis behind all the assertions in these human standards. And what you will find, if you really dig, is that most of them were, somebody had a notional idea and somebody else referenced it and then somebody else referenced it, and you can't get back to the original reference in most of these values for things like that are sort of non-measurable, what's tolerable volume. So we really have to question a lot of the values that are driving NASA studies to show that mission's impossible, because they really are often based on things that haven't really been tried. This is in LEO, obviously, and after launch. It's a pretty standard configuration that we've seen on Apollo before. The kind of thing that Orion is designed to do. This is all well within capabilities of the vehicles that are being developed, but to me a vision that is greater and more compelling and more sustaining. My biggest concern again is that we don't have a sustaining vision for these vehicles that are being developed, and it's critically important that we do, or they'll never get through administration changes. Look at how we almost lost it in the last administration change, right? That was really close. And for those of you who wish, anyway, we'll get into the politics. We do the burn, we separate, this is the configuration. And this is a very fundamental configuration. You see this a lot in Russian concepts. There's a habitat and a reentry module. This is a really, and it's the same as the last configuration we had. with the Venus Flyby. Don't you just love what the graphics guys can do these days? And these are the kinds of images coming back that with little microsatellites sending, maybe throwing a GoPro camera out every now and then, that really change the way we understand ourselves in relation to the solar system. You know, these pictures are incredibly significant, I believe, that the kinds of changes in our perspective of our place in the solar system are changed by these kinds of missions, the way Apollo 8 changed our view of the Earth in the solar system.
Is it possible to dim the lights so we can see the
video? Let me see if I can get something back. No, that's just, I'll see what I can do, okay? There's no more tech here, so I'll see what I can do. Keep talking.
All right. Approaching Earth, and then obviously Earth entry. These are a series of things that you've seen before. So one of the things that Dennis really cottoned onto very early on in this process was, if we're going to fly for 500 days,
Just keep talking.
and we need to test these systems for about that period of time. One of the teams today mentioned, you know, a 500-day test of the life support system. We've really got to get on it. The life support and the reliability and that you're really testing these systems is important. So Dennis invested significantly in. I'll go back through all the pictures after this. So Dennis really invested in the life support side, and in part because it's a pacing item. It's incredibly important, and the level of progress being made in this area is very small. So we concentrated on several of the really key subsystems. First in air revitalization, trace contaminant control, CO2 removal, CO2 reduction to get some of that oxygen back, and producing oxygen. So in the air revitalization side, we said, let's make these, and then we did 2 on the water side. So we put together 6 of the primary life support system functions in one laboratory, which, this will work backwards, in one lab, and we got all 6 of those functions working together at the same time. So we really pushed the integration and getting all these subsystems working along, and some were feeding each other. So we had a CO2 reduction system, we had an oxygen production system, trace contaminant control, and CO2 removal, all fundamentally based on technologies that are being used on ISS now, but 1 generation better. Because it's been long enough, we're at least a generation better. So in CO2 removal, we put together the system, and this is on the test data of CO2 going in, going out. What was new about this system was that rather than having a 4-bed system, we had a 2-bed system for you eco-sweeneys in the room. And rather than having 2 extra beds there just to remove water with 4 valves going, we used a humidity control wheel that pulled the humidity out of the stream and returned it to the cabin in a very simple way, much less moving parts, highly reliable. And we tested that and looked at its ability to capture water and give it back to the system and its duty cycles, and got to an 87% water recapture efficiency, and really beat it up in the lab. So then we had to go produce oxygen, and we used an all-vapor phase water electrolysis system. The system that's flying on station now uses liquid water and those phase separators. It gets very complicated, but the state-of-the-art in electrolysis now is all vapor systems in the stack. So we put that together and ran that to produce sufficient oxygen for 2 people over the course of several weeks. And it was a very steady system that really worked quite nicely. Again, much more simple. The surrounding hardware around that is what makes it so much better, because it's simpler. In trace contaminant control, we looked at formaldehyde, pneumonia, and carbon monoxide, methane. These are sort of the major things that we all put out and pollute our environment with, and we have to get taken care of. And We had far greater removal efficiency than needed. Again, this is a system based loosely on what's on station now, so we're pushing the existing state of the art. We're not trying to sort of revolutionize most of these things. On the water recycling side, the two big systems are the primary water processor, that's what makes your potable water, and the urine processor. And you can see there's lots of supporting systems around that, but that's basically the two major systems. And in one case, we really did make a major departure from current state of the art, which is in urine processing. And in water processing, we adapted existing technology to fulfill that need. So for water processing, essentially, we're using ion exchange cartridges and HEPA filters and a pretty standard suite of how to make good potable water, or water. Actually, what defines the primary water processor is the needs for electrolysis and how clean that water has to be. And we did all kinds of tests with all kinds of different chemicals to try to foul it up, and we couldn't. So we were quite happy with that. Then the urine processor is a step away from vapor cascade distillation. It's a very complicated system that takes urine and vaporizes it and condenses water and tries to do all this in a microgravity environment. We said, let's see if we can do this same distillation process, but with membranes. And so essentially what happens is you fill this fancy bag up. Sort of hard to see in this picture, but this is a bag that on the left you fill with urine. You put it in a fancy drying chamber, and the water selectively permeates through the bag, leaving all the urine solids behind, and you get that nice jar of drinking water at the end. And you would never know to drink it. And we've had blind taste tests that didn't know. When you tell them that they've been drinking the urine from just about every engineer in the company, you know, they sort of get a bit squeamish, but nonetheless. So in a series of tests, what you essentially get is, if you hold that membrane up to the light, you see some of the solids that get left behind, and you can refill the membrane. But what's really attractive about this is that all of those toxic contaminants are not in the air of the spacecraft cabin in microgravity. They're all contained very nicely. Again, I won't go through sort of all of the water quality results, but that again, it all worked quite nicely. And all of this has been published, by the way, of course, with foundation funding. All of this data has been published extensively for the community to leverage from the work that's been done. And then leveraging that work, we worked with NASA to say, what's the next generation of that membrane system? So we added some different membranes to make the permeation more selective, and we went to NASA and said, give us your worst. What's the worst stuff? And I said, that's easy. That's brine from station. So station has a vapor system that gets about 80% of the water out and creates this sort of nasty, tarry brine stuff with water in it, and it's been sterilized with acids, and it's a hazmat site in space. And so that's what's in the black jug at the left there. And we got a jug of it from NASA Ames. They were very nice. They drove specially down to Tucson with their jugs of concentrated, pre-treated urine. Wouldn't tell us who did, never mind. So we pump it into this bag. The bag fills up. We slide warm air over it, and we condense out water at the end. This system has been transferred to NASA Ames, and they're testing it as we speak. And it's another example of a line of technology that Dennis started, and we were then able to leverage that and move forward and provide hardware for NASA to test in a collaborative work with NASA. So this model is working. The model was demonstrated by Inspiration Mars in the work that we did with NASA, and we continue to do that. And so again, here's the water and the empty bag with solids behind, ready to fill up. And we're hoping that the next step on this is, of course, sending this system to the International Space Station to try out microgravity. The air inlet parameters that we used are actually the air inlet for the air handling system on ISS for humidity and temperature. So all we're hoping to do is just sort of plug this system into the air inlet of the ISS air revitalization system and just let the bags dry out the urine and treat the existing brine that's on station. So I hope that will work. So, I mean, just to, sort of in summary, probably most importantly, a lot of what Inspiration Mars did was really independently validate the need for SLS heavy lift for deep space missions. You know, maybe in some of the scenarios you've seen, it's marginal that you could get away with others. Maybe there's some scenarios out there, but we really found to do this simply and effectively, you really need an SLS, and that wasn't where we started, as Dennis said. We really started off thinking, well, how do we do this without? And ended up saying we really need it. And certainly the same is true of needing a deep space capsule. So in many ways, we validated the NASA program and provided one of the most independent program validations that has ever been done. Obviously 2021, I think, is a very real goal that the country, that's worthy of America. I mean, that's, you know, when you say to yourself, what should that next mission be? And maybe it's a series of missions to get there. It's got to be something that's really worthy of not only America, but our international community. The kinds of hard challenge that really gets people up in the morning and makes us proud of what we do. There's some people say, well, we shouldn't do the asteroid mission. And I think politically it's sort of silly to say either or. Certainly Phobos and Deimos are on the road to landing on Mars. Learning to operate around an asteroid and at these low gravity bodies makes sense. I don't think you have to say either or. And certainly the chart I showed earlier, there's lots of SLS missions where we can do both. So this isn't you have to say one or the other, but it certainly is we have to get going. And the work that was done to get that build there is great. And I'll be happy to answer any questions that you all have.
I just wanted to ask, what limits the idea of just sending one person and then having a lot of the mass requirements? You could do it with SpaceX.
So why not do one person crew?
500 days.
500 a day, one person crew. We looked at one person crew. It doesn't have the mass, so you have the amount of food. Water's being recycled. You don't really have the hardware because the incremental sizing of a system, you know, if one person or two person isn't that much. The two things that really drove me first off was operational safety of two people. I think it's critical to have that backup. And then which do you choose? You know, man or woman, right? I mean, you know, to properly represent humanity, as Dennis, this is actually Dennis's words, to properly represent humanity, you really need a man and a woman. So that's really what took us to 2 and 3, you know, anyway. Go ahead.
Is the SLS version you're baselining with now the 75 metric ton version or the 130 metric ton?
It's the, it isn't quite the 130, I think it ends up being the 105, so you have to do the real upper stage. This dinky thing they're putting on it now is embarrassing. So you don't have to have the advanced boosters, but you really need, you know, what you're really getting up there is a big, huge tank of hydrogen and oxygen with, you know, 4 L10s or something on the end of it. That's what this rocket's meant to do, and I shouldn't speak too much about what I think about the stage that's on it now.
That's in the bill also.
Yeah.
Second stage.
So we need that second stage for both.
But I read a couple of weeks ago that the Orion capsule is not scheduled to be finished until 2023. Is that false information? No?
Yes,
Yes.
that's not true.
Okay.
Yeah, 2021.
With man rating?
Yes, yeah,
So
absolutely.
when is it scheduled to fly the first time unmanned?
17,
Okay.
December 17.
Well, and on SLS, but unmanned flight is this year.
Yeah, well, flight December, but not on SLS.
Okay.
Skip Philip.
Is your flight then the very first flight of that upper stage?
Well, I don't think it should be. That's my problem with the dinky interim stage. That upper stage is really the horsepower that makes SLS work, and so we should be flying it right off the bat. So I just think the interim stage is, I'm sure the people who plan these things out have a good reason to do it. I think it's so important to practice using that. So.
2,000 heavies would be 106 metric tons.
When you get into the details of actually doing the burn with low ISP fuels, it gets, it's a lot harder to really make it work.
So it should be lifting another stage.
So now this is why we were so great to have all these different ideas presented today, because there's a lot of different ways to do this, and a lot of them work and have different amounts of issues. What we were finding in the analysis was that without a high ISP stage, you keep spending more fuel to get that low ISP stage up there, and the whole thing sort of grows uncontrollably. And so we had a really hard time closing with margin, because we need performance margin, we need boil off margin, we need all the margins that stack up, and you really say, I'm going to start with a concept and lock in the concept. If I'm going to do something really quickly in a locked in concept, I have to have all kinds of margin, because I know I screwed it up, right? And so to keep the concept from changing, you need to have lots of margin. And where we found was when we started adding margin in appropriately, and that was when we got the engineers who got Dennis and I to be honest about all this, we couldn't get around needing a big hydrogen-oxygen upper stage. Good.
How will a husband and wife team be chosen? Have you ruled out a reality series?
Sort of did. I mean, we did say to ourselves that they needed to have a history of working together. So, I spent 2 years and 20 minutes inside Biosphere 2, and with one of the crew members who became my wife afterwards, but I thought I knew those other 7 people pretty well. And we'd all worked together for 8 years building and designing Biosphere 2. And they were really different animals after about 6 months. So the team really has to be put in training environments that are long periods of time. Anybody who wants to do this kind of a mission is like a type A person, like gung-ho, I'm gonna go 500 days to Mars, da 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 da. And it's almost antithetical to the kind of person you really want to send on a mission of 500 days. And you sort of got to beat it out of those type A people. And it took about a year for us all to sort of, take a step notch down and say, what you really want to go to Mars is a bunch of, really, really bright couch potatoes. Go ahead. It's really more of an example than a hard decision. The MPLM, as other of the teams noted, is an existing structure that's been tested and used a lot. The Cygnus module is as well, and so the whole idea is to use an existing structure, but not a hard decision as to which one to use.
Hi. You said sending both a man and a woman would be a good positive humanitarian gesture. I agree, but I also assume you're going to be doing some testing and monitoring and fact-finding of your human occupants of the capsule. So my question is, what is the value added in your mind of sending both genders instead of just a single gender in terms of what you might learn about human endurance in space?
Well, I guess you could make the argument that if I have an N of 2 instead of an N of 1, I might learn a bit more. I think you're going to learn more by having 2 N's of 1s of different genders, because then you've really captured if there's a significant, hard biological difference. And there certainly are differences. Why are men having eyesight problems from ISS and women are not? So I think it's more important to get the two genders than to have a higher N number in this case.
For those of us who think we might get to go to Mars, at least at my age, I think I'm expendable enough to take a trip to Mars. Risk scenario that we have. What do you suggest that we what should we do to physiologically prepare ourselves for a trip to Mars? And what would you like to see in a person who is ready to go to Mars from a health standpoint?
I would leave sort of the specifics of the health standpoint to the doctors. Dr. John Clark is the Chief Medical Officer for Inspiration Mars, and is one of the great things about Dr. Clark is his attitude that, aside from very specific things that would rule somebody out, we need to design the mission to accommodate the specific physiological needs of the best qualified overall candidate. So don't make a lot of health issues gating. Decide what the risks are and work through them with each of your top candidates. And some of the most interesting near-term work really is some of the genetic work, looking at how people react to or respond to radiation, the long-duration studies that are beginning to go on at ISS. I think there's a lot of really interesting physiological work, and really, the cutting-edge medicine is something that Dr. Clark wants to demonstrate on a mission to Mars. How we use some of the genomics and specific medication designed for people's specific genetic makeup, and demonstrate the efficacy of these things on a mission to Mars. So I don't know how much I'm sure I can keep going all night, so you tell me when to stop.
Let's go 10 more minutes.
All right, 10 more minutes.
In your ideal scenario, how many teams would you like to train for the mission?
Oh, in the ideal scenario, how many teams would I like to train for the mission? Well, the number 5 to 10 pops to mind. I think, so at Biosphere 2, we had an initial selection of 30, and that was pretty rapidly wheedled down to 15, and it got to 14 because one person had a health issue, and we stayed there for quite a while, and then the final down select to 8. In some ways, we didn't down select early enough because we weren't training as crew members. We were also managers on the project. So there's a trade-off between really training that many people and giving them the attention they deserve, and having some of your backup crews. So I think you probably want to pretty quickly whittle down to maybe a primary and 2 backups or something like that, and really put attention into getting them the training they need.
So this is concerning the gray water processing unit that you mentioned. Do you have any data? I know the work is ongoing about the longevity of the membrane, how many uses it gets, or the percentage of water recovered for your system?
We do have data about percentage water recovered, and that's been published. And we have data on the transmission rate. So percentage of water recovered is in the 98, 99. You probably saw a couple of 101s up there, just given the math. The membrane is essentially a Teflon membrane that has had a lot of, we've reused them several times and really haven't found end of life yet. It turns out that you get such great mass benefit just for single use that it's worthwhile not even reusing the bags, but we haven't yet found an end in sight to that, and that's sort of ongoing work. But it's fundamentally an ion exchange that moves the water through the membrane, and so unless there's another ion that gets in the way, it should work for long periods of time. These membranes have been in industrial use for 30 years, so it's a long history too. Yes?
Talk about the membrane and screening the urine. So what about trace chemicals such as drugs and so forth that the astronauts may be taking? Are they screened out, or do they start to accumulate in the water supply?
Yeah, they are retained in the bag. So it's a selective. The way the membrane works is there's sulfonic ion chains in the membrane that hydrate. And so there's a very small number of other chemicals that will also bond with the sulfonic acid ions, and they then hand the water molecule across through the membrane to one on the other side where it evaporates again. So it's incredibly selective, and sort of organics like a drug do not move through at all. Radiation shielding? The question is, what do you do with the brine that's accumulated? Well, I mean, you know, it came from, so one of the funny things that I didn't quite hear this team's get today about water and radiation shielding is that all this stuff came from stores. So you really can just sort of put it back where you got it, you know, in a different box, obviously, but you know, the mass is the same, the volume is fundamentally the same, but what's interesting about bringing food with you is you're bringing carbohydrates. And so that ton of food, or 2 tons of dry food, is actually, a lot of it's water. It's great radiation shielding, and you can, and so you're adding water to the system. As the people eat the food, they're producing the hydrates that comes from oxidizing the carbohydrate. So as long as you can keep recycling the CO2 that comes out, you're adding water to the system. So the analysis that people showed today where the amount of water in the tanks gets less and less and less really doesn't happen at any decent level of recycling. It actually gets more and more and more because you're taking water out of food stores, metabolizing it, and putting it in your water tanks.
Could you give your thoughts on the amount of meaningful work that the individuals will actually have during their mission? Just given that there will be no landing on the surface and the extended duration of limited volume and crew size, what are your thoughts on meaningful work?
So the question is, what are my thoughts on meaningful work that the crew will do for this long duration where there isn't a landing, so there's stuff to do? I thought Dennis put it very elegantly, you know, make this life support system need a lot of maintenance, because then you're always practicing fixing it, right? You know, so there's going to be a lot of, you know, Dennis called it the 57 Chevy, and we rib each other a lot about that. But it's, you know, keep the systems that simple, and don't worry about manual labor, because it's that automation that breaks down. So ISS does have one key difference in that there's a desire to automate everything as much as you possibly can, because the reason astronauts are on ISS is to go do science, right? So I don't want them spending all their time maintaining the life support system, or where are they up there? In our case, it's fine to have them spending a lot of their time maintaining the life support system because it buys simplicity in the system. The automation that ISS needs in a lot of cases creates complexity that we don't otherwise need. So there's that. Then when you look at the long list of medical studies that the doctors want to do, they're going to be poking each other a lot. And then between that and food preparation and exercise, and with any time that's left, the great thing is communicating back to Earth. I mean, imagine if you were sitting as a middle school student in an assembly and you were actually asking questions of a person on their way to Flyby Mars. Now, obviously, you know, you go to the assembly, you ask the question, you come back 20 minutes later, but I mean, you get the idea that you know, that kind of communication, those interactions, that's what blows the mind of the kids that we need to inspire to get into science and technology, to show them the amazing things that science and technology does. That communication back to Earth, that human link, that what did you feel like, what is it, you know, what is it like to be there, to have Earth just this little tiny Carl Sagan pale blue dot. How weird is that? I mean, what can it, it's hard to fathom what it would feel like to have Earth be a star like every other star. These are, you know, just taking the time to communicate that back to Earth is going to be one of the most inspiring things I think they could do. So with all of that, I think I've answered your question, I hope.